Good morning students, welcome to Basic Electrical Lectures and we are doing Module 3 Single Phase Transformer. In the last lecture, that is class number 4, I explained EMF equation of a transformer derivation. Okay, after that next your syllabus topic is losses in a transformer. Okay, and it is class number 5. So based on that topic, so we can predict question on that particular topic asked in a model paper for 8 marks. So what is that question is? List different types of losses in transformer and explain each one in brief. So they asked for 8 marks. So same question we can predict for 4 to 8 marks. Okay, we can start this. See, losses in a transformer are classified into 2 types. So losses in a transformer are classified into 2 types. One is called iron loss. It is also called core loss. And another name, that is constant loss. Iron loss is also called core loss and also called constant loss. And another one is variable loss, that is called copper loss. So copper loss or variable loss. Both are same. In iron loss we have again 2 types. Okay, one is hysteresis loss and another one is eddy current loss. Similarly, in copper loss we have 2 types. So copper loss takes place in the conducting material. So in transformer we are using conducting material as a copper. We can also use aluminium. Under that condition it become aluminium losses. However, copper we are using most in all the applications. In all types of transformer we are using copper as a suitable conducting material for wounding the conductors around the core, because it is highly malleable and ductile. So if I use aluminium conductor, so I cannot bend the aluminium conductor according to my requirement. So due to that we are not using much aluminium as a conducting material, as a winding material for transformer construction, whether it is core type or shell type. Okay, so fine. So copper loss. So popularly we are using copper as a material, winding material, hence we call copper loss. So in that we know that transformer there are 2 windings, primary winding and secondary winding. So primary means primary copper loss and secondary winding we can call it as secondary copper loss. Primary copper loss and another one is secondary copper loss. See, the primary copper loss is denoted by P1. So primary copper loss is given as I1 square into R1. So primary current square into R1 is nothing but primary resistance. Similarly, the secondary copper loss is given as P2 is equal to I2 square into R2, where I2 is called secondary current and R2 is called secondary winding resistance. Okay, so therefore the total copper loss is given as primary copper loss plus secondary copper loss. And another name for copper loss is variable loss. Why it is called variable loss? Because when the transformer is loaded, so actually what do you mean by secondary winding? The winding which is connected to load is called a secondary winding. If that load is on secondary side, if the load increases, the secondary current increases. If the current increases, what happens? If the current increases, okay, the copper loss also increases. Or varies. So the transformer secondary varies as load increases on the secondary side. If load increases, current also increases. If current increases, losses also increases. So got it? So depending on the loading condition of the transformer, your copper losses continuously varies. Okay. And what about primary copper loss? See, the primary copper loss will going to vary, okay, with respect to secondary copper loss depending on the turns ratio. If the secondary current is affected, primary current is affected with respect to turns ratio. Okay, got it? So if secondary current increases, primary current also will going to slightly varies. So primary copper loss also varies. That's why this copper loss is called variable loss. So next we can move into iron losses, detailed explanation of iron losses. See, the transformer core is made up of a solid iron core. Okay, earlier they are using solid iron core. So if I using that solid iron core, we are going to found these two types of losses. Okay, and however we also have a solution to how to reduce this hysteresis and eddy current loss. So we can move to detailed explanation for hysteresis and eddy current losses. See, iron is nothing but a core. The transformer core is made up of iron. If any loss is occurring in that is called core loss or iron loss. But they are used the word constant losses. See, why it is called constant losses means these losses does not depends on load currents. Okay, these losses are independent of loading conditions. Whether transformer is loaded or not loaded, these losses will not get any changes. It remains constant. However, this losses also varies by the internal parameters, within the internal parameters in the transformer. Okay, so we can discuss in detail. The losses occur in the transformer core is called iron losses. In that we have two losses. One is hysteresis loss and other one is eddy current loss. Guys, please pause the video and then copy down this chart. Okay, so shall I erase? So next we are going to discuss detailed about hysteresis and eddy current losses. See, iron losses are divided into two types. What is first one? Hysteresis loss. Hysteresis loss. Okay, it is denoted by pH. Okay, hysteresis losses are denoted by pH. So the meaning is when an alternating current flows through the winding, it undergoes a cyclic process of magnetization and demagnetization process. So when I give supply to the windings, okay, an alternating current flows in that. That current undergoes a cyclic process of magnetization and demagnetization. This word is very, very important. Okay, magnetization and demagnetization process. Magnetization and demagnetization process. Okay. See, during this process, there is a tendency that flux density going to lag the magnetic field strength. Okay, so flux density is denoted by B and magnetic field strength is denoted by H. Okay, so we can understand better way regarding hysteresis losses by plotting BH curve. So generally the word tendency is nothing but hysteresis. Okay, so your flux density going to lags the magnetizing field strength. Okay, so that tendency is called hysteresis. Okay, got it? So we can better understood hysteresis loss by plotting BH curve. Okay, so we can plot that curve and we can understand a little bit. Since you are first year students, don't go much in detail. Okay, so this is flux density B and unit of flux density is Tesla, and this is magnetizing field strength. H is nothing but magnetizing field strength, and the unit of magnetizing field strength is ampere turns per meter. Guys, during positive half cycle, because when I give supply to the winding, that is AC supply, it will have positive half cycle and negative half cycle. So during positive cycle, what happens? See, when magnetizing field strength is zero, at that condition, your flux density going to lag the field strength by some amount. Okay, so your flux density will be here. Flux density is having some amount of value when there is no magnetic field strength. Okay, so got it. So now, as soon as your flux density, this magnetizing field strength increases from zero to positive value, and finally it reaches to maximum value. Okay, this value is called maximum magnetic field strength, H max. Okay, see guys, at this point is x-axis is hysteresis, y-axis is flux density. When hysteresis x-axis is magnetic field strength. When magnetic field strength is zero, at that condition your flux density has a tendency lag behind magnetic field strength. It is having some amount of value. With the help of this flux, flux density, the hysteresis loss is slowly increasing. Now at this point, hysteresis loss is zero. Finally it reaches to positive value, and still it is increasing, and finally reaches to maximum value. Okay, and after that it reaches to maximum value. Next, what happens? Negative cycle came. Okay, so once your alternating current reaches to negative half cycle, the magnetic field strength decreasing, finally it becomes zero. See, at this point, what is your x-axis? At that point, 0. But flux density is maximum. So during negative half cycle, your flux density leads the magnetic field strength by some amount. See, when this is returning back is negative half cycle. So finally, the magnetic field strength will become 0. See, the magnetic field strength, it lies on x-axis. What is this magnitude? So 1 minute. It reaches to maximum value during positive cycle. Once negative cycle applies, so the magnetic field strength decreases and reaches to 0. Okay, during that time the flux density is having positive value. But when flux density becomes 0, see at this point y-axis is 0. At that condition we have magnetic field strength. So finally it reaches to negative peak, and again it reduces to 0. When it comes back to this position. Okay, so this process will be continuous during positive and negative half cycle. So this, I can give some namings: A, B, C, E, and this point is E. See guys, the curve A, B. Take this one as D. A, B, D, C. This entire portion is called energy stored. Okay, during positive cycle, energy will be stored. Okay, and this portion is called energy released. Okay, energy released. Okay, got it. So what I written, this entire shaded portion is the process taken place during positive half cycle. Okay, got it. So this thing and all you need not to write in exam. Since you are first year students, you just write a word for hysteresis loss. When an alternating current flows through the winding, okay, it undergoes a cyclic process of magnetization and demagnetization process. See, during this process, okay, energy will be stored and energy will be released. Okay, during magnetization process, energy will be stored. During demagnetization process, energy will be released. But due to difference in this energy, see, energy stored is more compared to energy released. Due to difference in the energy, then you will get the net losses during each half cycles. So this losses will going to produce more heat in the transformer core. Okay, that heat is in the form of power loss. Okay, so called hysteresis loss. Only for understanding purpose I written this BH curve. Okay, got it guys? So next is pause the video and then copy down. See, whatever I dictated sentence, that you must listen and then write it. Okay. Only one key point I am telling once again. When an alternating current flows through the winding, it undergoes a cyclic process of magnetization and demagnetization process. Is called hysteresis loss. That much is sufficient. Okay. Don't write all these things. Only for understanding purpose I have written this curve. Okay, BH curve. Okay, that is called. See, during magnetization, energy will be stored. During demagnetization, energy will be released. The difference in that energy will going to produce hysteresis loss. That is called net power loss. That loss will be going to dissipate in the form of heat. The transformer core will become more heated. Okay, got it? So hysteresis loss is given by the equation. Okay, the pH is equal to KH Bn to the power of n into F into V. F into V. This is hysteresis loss equation. See now, where this please write this one as KH. Since we are discussing hysteresis, we should write KH. See, where KH is nothing but, write down. Please write down. KH is nothing but hysteresis coefficient of the core material. Hysteresis coefficient of the core material. And this value varies from 0.025. The hysteresis coefficient for cast iron, okay, cast iron or cast steel varies from 0 to 0.25. This is the hysteresis coefficient. Similarly, the hysteresis coefficient will be 0.001 for silicon steel. For silicon steel. For silicon steel, the value of hysteresis coefficient will be 0.001. And then Bm is called maximum flux density produced in the core. Okay, and its power n, the power n is nothing but a constant. Okay. So this constant depends on the core material. Which material you are going to select, that value going to changes. Initially, it values varies from 1.5 to 2.5. So in my notes, I have written Bm to the power of 1.67. Bm to the power of 1.67. See, that is called constant n. That n varies from 1.5 to 2.5. Okay. You can write like this, otherwise you write one value directly there. Okay, that is also correct. So then next is F. F is nothing but frequency in hertz. What do you mean by frequency? The frequency of flux reversal. Alternating flux keep on changes, positive cycle and negative cycle. That is called frequency of the magnetic flux reversal. Then V. V is nothing but volume of the core material. Volume of the core material. So remember, in Viva they will ask, hysteresis loss is directly proportional to the frequency or inversely proportional to the frequency. Such things they are going to ask. So you should remember, hysteresis loss is directly proportional to the frequency. If the supply frequency changes, hysteresis loss also changes. See, in this equation there is no current parameter. There is no current parameter. So therefore it does not, current parameter slightly changes when load occurs. Current value changes when load occurs. Since hysteresis equation is independent of loading equation, loading current, therefore this losses will not varies with respect to whether load is there or not. It won't changes. It changes within the design parameters. Okay, material. Which material you are going to select? That material, the losses keep on varies. Okay, got it? So fine. Hysteresis loss depends, directly proportional to the frequency. The next is eddy current loss. Guys, pause the video and then copy down. Next is eddy current loss. See guys, we can minimize the hysteresis losses by selecting ferromagnetic material. Hysteresis loss can be minimized by selecting ferromagnetic material. What do you mean by ferromagnetic material? It means the material should have low hysteresis coefficient. Such type of material we have to use so that we can reduce the hysteresis loss. Okay, we have to use which material? Very good, ferromagnetic material. Example, silicon steel. Okay, fine. Next is eddy current loss. See, eddy current loss are nothing but, see, only simple word you write. Don't write in detail, but you can understand in detail. In exam you write only what is the key point I am going to tell. See, eddy current loss. So this losses will going to happen within the core itself due to circulating currents. Okay, whenever the windings are excitable supply, it undergoes a magnetic field is created. Okay, that magnetic field will going to link with the core material. Okay, so core material will have good conducting properties. Core material. Okay, so that conducting material going to cut the magnetic field and hence EMF will be induced. That induced EMF will going to circulate the current within the core itself. So that current going to produce more heat. Okay, so that heat is nothing but power loss, so called eddy current loss. Okay, so eddy current loss is nothing but the circulating current flows within the core itself. Due to that, power losses increases. Is called eddy current loss. Like that you can write. See, suppose if I use a solid core. Okay, this is a solid core. So this the eddy current loss keep on circulating within the core itself. Now I want to reduce this currents will going to produce a power loss, high power loss. Why means the core material, preferably we are using iron. Okay, iron is having low resistance. This current will going to pass faster and produces more losses because of low resistance of iron. So however, we can reduce this losses by making number of laminations. Instead of making this big solid core, so we are going to cut this solid core into several laminations. Generally, the thickness of this core, suppose if you consider 1 centimeter, 1 centimeter is the thickness of the core, you do it, break that core, okay, like in this form, 0.25 mm. Then it becomes what? A thin plate, a thin iron plate. So by doing like that, now the 0.25 mm may be like this. The 0.25 mm may be like this. So within this, the circulating current will keep on flowing, and that current will be very, very less. Okay, got it? So, and by making this, we can reduce the eddy current losses by increasing the number of laminations, okay, of a solid core. We can reduce the eddy current losses. Suppose if I not cut all the laminations, if I directly use a solid core, then your core will become more and more heated. Okay, got it? So that can be reduced by using n number of laminations, by increasing the number of laminations. So means instead of putting a thick 1 centimeter iron core, don't do like that. Instead of doing 1 centimeter, you divided this 1 centimeter solid core into several laminations. Okay, and join all the laminations and stamp it together, then you will get a required size of the transformer core. If you do like this, eddy current losses can be reduced because the path for the circulating current will be lesser if you reduce the thickness of the core laminations. Okay, So if I make the thickness of core lamination larger, then current will increases. Okay, got it? So eddy current loss is given by the equation Ke Bm square F square T square into V. This is the formula for eddy current loss. See now, what do you mean by Ke? Eddy current constant of the core material, and Bm maximum flux density. F is called frequency of flux reversal, and T is called thickness of core laminations, and V is called volume of the core material. See, thickness of the lamination plays an important role in reducing the eddy current lamination. If the thickness increases, eddy current losses increases square of the thickness of the laminations. Okay, got it? So don't use a larger thickness of laminated core. Okay, sorry, solid core. Don't use directly solid core as a transformer core. Okay, instead of using a solid core, you used that same solid core, you cut into number of laminations and then you can use it, so that we can reduce the circulating current flows within the core. As long as you reduce the circulating currents, we can reduce the eddy current losses. Okay, got it? So in Viva they will ask, you should say like this: eddy current loss directly proportional to the square of the frequency. See, if the supply frequency 50 Hz, then what about your eddy current loss? 50 square. Okay, what about hysteresis loss? Directly proportional to the supply frequency, but eddy current loss proportional to square of the supply frequency. So got it? So see here, eddy current loss also not depends on current. So therefore this losses is independent of loading conditions. Hence this losses we can call as constant losses. See, once the transformer core is designed, okay, then you cannot reduce the thickness of lamination. You cannot reduce flux density of the core material, and you cannot change the eddy current constant. Once it is designed, that losses is fixed. Okay, so it is called constant losses. Okay, during design only one time loss. Okay, whether transformer is loaded or not loaded, the iron losses will become constant, so called constant losses. Okay, got it? So summary. So guys, pause the video and then copy it out. What you can write the definition for hysteresis loss? When an alternating current flows through the winding, it undergoes a cyclic process of magnetization and demagnetization. Okay, during magnetization, energy stored. During demagnetization, energy released. The difference in the energy will going to produce net power loss. This power loss going to heat the core is called hysteresis loss. Okay, got it? We can understand better hysteresis loss by plotting BH curve. Okay, how we can reduce hysteresis loss? We can reduce hysteresis loss by using ferromagnetic material which is having low hysteresis coefficient. Example, silicon steel. Okay, and how to reduce eddy current loss? What do you mean by eddy current loss? The circulating current will circulate within the core itself. That going to produce power losses in the form of heat is called eddy current loss. How we can reduce eddy current loss? We can reduce eddy current loss by increasing the number of laminations and reducing the thickness of the core material. By reducing the thickness and increasing the number of laminations, we can reduce the eddy current losses. Okay, got it? So what about copper loss? Copper loss depends on the loading condition. It is also called variable loss. In Viva they will ask, explain losses in a transformer. You can explain all those things. You just list out the types of losses. Okay, that going to impress the examiner. Okay, so thank you. Have a nice day, guys. Please subscribe and give like to our videos. So in the next class, I am going to explain basics related to solve problems on EMF equation. Okay, so losses in a transformer is a very easy topic. Next we are moving to efficiency. Once we know the losses, then we can move to efficiency. Okay, so guys, 1 minute before leaving. So the total iron losses is a sum of hysteresis loss and eddy current loss. And total copper loss is the sum of primary copper loss and secondary copper loss. Addition of these two, iron loss and copper loss, is called total loss. Okay. Same thing I will repeat in the next class. While doing efficiency topic, I will take the losses concept. Okay guys. So have a nice day. Take care. Bye bye.